Who started that?
Should I give? I have no idea what I'm doing right now.
Okay, so so let's you.
Nicola, go ahead.
Okay. Hello again. Welcome to the fourth seminar in our Waterhackweek Cyber Seminar series. I am Nicoleta Cristia. I am here with Emilio and Yifan at the University of Washington eScience Institute. And Emilio and Yifan will talk today about data access and time series statistics. Enjoy.
Hi, well, thanks for coming. I'm Emilio Mayorga. I'm at the Applied Physics Lab here at the UW. I am originally, or my original background is in aquatic biogeochemistry, rivers and coastal environments, but I've moved over a lot into data sciences. And Yifan Cheng is from civil engineering and environmental engineering, but he'll introduce himself later when he gives his bit of the presentation. You want data, you're ready to start your research, you need data. How do you find it? Unless you're collecting it and doing all your research with the data you collected, and this day and age that's rare. Where do you find the data and how do you access it? In the first place, data comes in all shapes and sizes, and it can be very heterogeneous. The spatial representation can be very different, from points like a weather station to a gridded data set like remote sensing, for example, or a model. You can also have in terms of the time dimension, your research question may lead you to need a long time series or to emphasize near real-time data or high frequency. Oh, just a second. It's covering that button maybe. Okay. Sorry, we had a technical issue here. Or to require high-frequency sensor data. So you sort of some of the questions that you'll be posing yourself as you decide that what data you need and where you might go to find it. Another very important consideration is whether your research involves, for example, work only within the US, or whether it's international, you have field sites at several countries abroad, or whether it's global in scope, like modeling across the entire globe. Also, do you need mainly the results of academic research, or are you likely to need government monitoring and research results? What is your domain? Water, and this is Waterhackweek, but water is pretty broad and umbrella. Are you dealing mainly in the atmospheric domain, surface water, or groundwater? And what variables are you actually interested in? No, need just a second. Okay. So where do we go? And of course, everyone will probably say first, Google. And yeah, Google is reasonable, but if you just go to the plain Google search, that can be pretty overwhelming, and you'll be flooded with irrelevant results that have nothing to do with data, or maybe not even your topic. One other Google component or tool that is emerging, it's called Google Earth Engine. And it's really fantastic for remote sensing data, for finding it and processing it very efficiently. But it's not really there yet, as far as I know, for site time series or site data. That may change in the future, but as far as I know, it's not the case yet. But there's a new Google tool that was unveiled, and it's still in beta mode early last fall. It's called Google Dataset Search. How do I go to?
Yeah, just click it.
Okay, and it'll open a new window. Sorry. I don't know if you've seen it. It looks just like normal Google, but it focuses specifically on scientific data or other kinds of data. So for an example, I'll Google Seattle snow, because that's where we're living here right now. And you see that the way the results are organized are quite different, are much more organized in structure. So this is becoming very promising, and you may want to use it as part of your set of strategies for finding data. I won't talk much about it. Go back to.
Oh, sure. Yeah.
Sorry, we're Okay, give Google Dataset Search a try, but it probably won't meet your needs fully just yet. And the reality is that there's no single catalog that will meet all your needs or any one person's needs for search, discovery, and convenient access to data, and especially that can work across all domains of water research. So where you go will probably vary depending on the specifics of your research question. Some systems are good broad starting points, though, like Google Dataset Search. Some systems make it easier to identify, ingest, and use the what is often called granular data, meaning the actual data values, what you actually want, consistently across sources, while others stay targeted at what is often called a data set and metadata level. In other words, a description of what data is collected that doesn't get you to the actual data values. So for example, if someone is describing or the USGS NWIS stream monitoring system across the entire nation, so it's a pretty large data set, could be described as a single data set. And some systems may present it to you as a single data set without telling you where the individual points are. Just on your own time, you may want to take a look at this page that does a good comparison between two systems that have a good contrast. One is the CUAHSI/Hydro client that I'll get into, and Data One that I won't get into very much, but it's a very useful and important broad catalog that focuses on ecology. Every system has a pros and cons then. Another thing to keep in mind, and we'll get into this a whole lot more soon, is that most catalog systems, most likely than not, you'll first see it as a user interface when you go online, and that can be, it is extremely useful if it's well built for interactive browsing. But most good systems also have what's called an application programming interface, or API, so that you can access and query its catalog and get data, if it allows you to do that, via code. And we'll definitely get into that via Python code. Typically, the user interface is easier to use, so you can get going much more quickly. But the API facilitates repeated tasks, large queries, reuse, and that important topic, reproducibility. So what should you be thinking about, or as you're considering, as you're developing your strategy to find the best data? One is just clarify to yourself what type of data you actually need. Sorry, I just realizing that I don't know if this. Anyways, I don't remember saying this, but this we're struggling a little bit with the presentation system. This seminar is focused on point time series, as opposed to gridded data set. Next week we'll be talking about gridded data sets. So points as in weather stations or other data that can be represented as a point. For example, a cell in a grid could be represented as a point. And also, it's worth noting that because of Yifan's and my own interest and background and expertise, we'll be focusing mostly on surface waters. So keep that in mind. Anyways, make sure you understand what kind of data your research question requires. Also, sure, we're here to talk about cyber infrastructure and fancy things, but don't discount the value of talking to your colleagues. That's still a great source for finding where to go get data. Like I said, do try Google, but there are other systems that are more specialized that may still be broad, but focused on earth sciences, hydrology, etc. And we'll talk about those here. And then ask yourself some questions. Does the catalog that you're considering make it easier to actually access the data in a consistent data format across data sources? Or is it focused at that course level, just data sets, which is not to say it's bad, it's just it won't solve all your problems. But again, no single system will. Check out each individual data provider's website to see if they have what you need. For example, a Noaa climate agency, or try to find a system or a tool that can let you query across multiple data sets. Are you considering, or do you think you'll be doing manual file downloading, or are you going to access it via code or programmatic access? When you go to the provider, what options do they give you? Typically, they give you multiple options. So check that out and find the one that suits your need best. See if there are code packages that span multiple data sets and can handle the data sets you're actually interested in. because that way you don't have to learn multiple and install multiple packages to get your work done. It's unlikely that you'll find one that covers all your bases, but do your homework to save yourself some time. As you're considering using any given package, consider whether it's fairly easy to use, well documented, and has plenty of examples. And also, because these tools are typically built by the community, see if there is an active community of users and developers around it. Otherwise, it might be a stale package that has been abandoned for 2 years, and you'll be wasting time. Think about what parameters you're using and whether the data source describes these parameters well. Very often, parameter labels and their meanings are quite different across systems, and you may spend quite a bit of time reconciling those differences, and let alone units, of course. How do I thank you, perfect. Is it control?
Command minus. Or command,
perfect.
Yeah.
Okay. So some of the catalogs we'll be focused on there are 2 CUAHSI systems. The main one we'll be focusing on is the HIS, what I call HIS Hydro Client. Hydro Client is the data.cuahsi.org. It's a web application, and we'll be checking it out a bit, but I encourage you to look at it and play with it. So it's a tool that facilitates discovery, visualization, and download. So it lets you get to the data directly for site time series, although there are some model output from a wide range of sources. And that's one of the key aspects of this catalog, that it's not just one agency. It's multiple sources, mixing both government agencies, as well as academic research. Behind this user interface, there's a catalog system, a backend database, if you will, that I'm calling here for consistency HIS Central Catalog, or HIS. We'll be accessing that catalog via APIs, via code. In other words, you can get at this data either via Hydro Client or via an API. HydroShare, I won't touch on it very much because you've already heard about it in a couple of presentations. If you work with surface water in the US, NWIS, you almost certainly want NWIS, unless you work in small streams. It's a fantastic system of a data archive and current data. Check it out, but we'll be exploring it quite a bit. And it does both water quantity and quality on surface waters and groundwaters. Another set of sources that you may not have considered is that this evolving set of networks of or observatories of field sites. There's NEON, which is a major NSF investment, sites across the US for the long term. LTER in biology and ecology, the critical zone observatories in earth sciences, and GLEON, which is the Global Lakes Observatory, and that is global. All the other ones are mostly US based. If their sites happen to coincide with your own area of interest, then they can be a wealth of data, and we'll explore some of them a bit. And the last one is a tool that I've been involved in developing it, but it's a broader team. It's called Model My Watershed, or Monitor My Watershed. It provides a user-friendly search capabilities that actually brings in, in and of itself, it doesn't bring in new data. It provides access across 4 catalogs. So it makes it easier to search across catalogs, or some specific set of catalogs, and that's HydroShare, the HIS Hydro Client Synergy, which we'll get into, and the Water Quality Portal. And it has some integration with HydroShare. There are other systems that that you should consider, and I won't get into it much, but keep in mind that all these materials will be available to you, or to everyone, by tomorrow or so. So this is a resource that you can use tomorrow and on the Waterhackweek event and in between. We won't be using climate data, but I'm sure many of you are interested in it. So I wanted to at least put down some resources that you may find useful. And probably the first one you'd want to go to is the Noaa Ncdc land-based station data, that mainly US data, but it covers also global data sets. Multiple data sets by a single, it's a case of a multiple data sets by a single agency provider. They do provide multiple access mechanisms, both a UI, you'll hear this term REST, but basically an API, custom API developed by them, as well as standards-based APIs. This Python package called Olmo that we'll be using a lot also has readers for this. So there's an independent package that has readers for a couple of the data sets from Ncdc. So it's a good exemplar of what we're talking about. There's also a nice data set from NASA, DayMed, that has characteristics that you may find useful. I'll take a quick look at this just so you see what we're talking about. So it opens another window, right? Okay. So we've gone to Ncdc land-based station data, and you'll see that it's organized by data sets. So because of the nature of the programs and how they monitor. So you'll have to, if you're interested in this data, you'll have to figure out which data set is relevant to you. And how you access data may vary a bit between data sets. And this is they have this system, Climate Data Online, that I haven't used because I don't work with this data that much, but it looks like it's nicely browsable, but it also has an API that will, well, we won't use this one, but it's a very, sorry. Okay. Can you go back to the presentation?
Okay, sorry.
It's an excellent example of what you'll encounter in the best of cases, where they let you access data in multiple ways. And it's broken up into different data sets. Okay, so as you know by now, hopefully, Waterhackweek emphasizes Python. And we'll be diving deeply into code, probably the deepest so far in the series of seminars. So I wanted to just briefly list or lay out the core packages for what we're doing here. Now, I know that Tony at last week's seminar used and talked a bit about Pandas, and hopefully you have heard about Pandas already and have used it. This is not going to be a thorough presentation about Pandas, but we'll be using it a lot. So you can think about Pandas as the backbone of this presentation, because we take all the data that we take, regardless of how it's originally organized. Both Yifan and I first get it into Pandas. It's a tabular data structure that has powerful tools that are really nice and easy to use and convenient. It brings in lots of functionality from other core Python tools that include read-write, data organization, exploration, cleaning and summarizing your data, which is a lot of what we typically do, and folds in things like NumPy and matplotlib plotting. Now, GeoPandas builds on top of Pandas, and it adds geospatial capabilities. And like Pandas, it also incorporates multiple very useful open source geospatial tools, and they're easier to use. Matplotlib plotting will be done here a lot, and Tony covered that quite a bit last week. I mentioned already the Olmo data package. For what we'll be presenting today, that's what we'll be focusing on, because it's a great example of a package that spans multiple data sets. And for the surface water data that we're interested in here, that Yifan and I are interested in, it's great. So time series is the title of the seminar, and it's useful to keep in mind that, and Yifan will be talking a lot more about or hands-on presentation on handling time and doing summaries, etc. But it's useful to keep in mind that it can be pretty confusing in Python to keep all the different datetime handling and object types straight. Python itself, the core Python, has its own objects for handling and tools for handling datetime. And they're nice. They're not perfect, but they're nice. But then when you bring NumPy, NumPy has its own datetime object. And Pandas introduces its own that builds on NumPy. That's called timestamp, and that's great. But very often, if you start with a CSV file and you read it in some way, you may be going back and forth across these types and having to convert it. So we won't solve all the problems here, but it's important to keep it in mind as you're handling time. Time zone handling can be a pain in the neck, probably in any language, but definitely in Python, it can be tricky. We won't get a whole lot into it, but I just wanted to make you aware. And I put a couple of links there to some resources about the pains in Python with daytime handling and solutions. So why Pandas timestamps are great and so on. So good luck. Okay, so we talked about some useful strategies for searching for data. And once you've identified your data sets, and now you just need to be able to get them and ingest them, I wanted to lay out some useful strategies or approaches or tools for getting and ingesting the data. And again, these are both a listing of tools and kind of questions to pose to yourself. First is, did you end up just doing manual browsing and download of files? And that means that you'll have a collection of local files that you have to dig through. You should consider also that there's this great Python package called request for general access via, basically you pass it a URL or a link. It's more than that, but you can think of it that way. So within your Python code, it lets you access remote data, and then you have to massage it or beat it into submission, I guess, once you get it into your Python environment. You may hear about other two command line tools, wget and curl, that do something similar. Now, Pandas also has a function called read CSV, which is a misleading name. You might think it's just for reading a local file and just CSV, but it's much more than that. You can pass it a URL, so you can read from anywhere in the web. But also, it's not just CSVs. It's basically a Swiss Army knife for any ASCII file, any delimiter, almost any ASCII file. So keep that in mind, that it's a very useful tool for getting data. You'll also be seeing quite a bit as you explore different sources of data that there are APIs. We saw that with the Ncdc case, the CDO REST API. So very often there will be custom web APIs from a data provider. We'll be showing an example based on the Neon system on what to do with those. Often this REST APIs, and don't worry at this time about knowing exactly what makes a web API RESTful, but often these are fairly easy to use, but they can, because they are typically customized by the data provider, they can be highly variable across systems. Other strategies for accessing data involve the use of standards and resources that were built as community standards. There are APIs that are based on standards. One is OpenDAP, another one is from the Open Geospatial Consortium. Well, not one, but a set of web services or APIs. And we'll be focusing here on one called CUAHSI Water One Flow to access data. You don't need to know details, but you just be aware that we're using that behind the scenes. For formats, there are also standards for how you organize data in a file or in a chunk of data. The one we'll be looking at the most here is WaterML. But keep in mind, because it can get confusing, that there are actually two flavors that are very different. Well, not extremely different, but in practice, they're different enough. One is the original or traditional CUAHSI WaterML 1.0 or 1.1. And the other one is the OGC WaterML 2. We will only be looking here at the CUAHSI WaterML 1. NetCDF is a powerful format also, and you'll encounter it a lot, both for site data, but especially gridded data. And we don't have any examples in this presentation, but next week you'll hear tons about it. And then there are also different formats for metadata standards. I put a link there to an old CUAHSI page. CUAHSI people might cringe that I added that link, but I think it's still useful, and I couldn't find something as useful as that single page. And that describes the CUAHSI set of standards. And again, the value of standards is that they enable reusability across multiple data sources and systems, as opposed to having to kind of relearn, look for the documentation and relearn everything for each data source, which can be a real pain in the neck, a lot of wasted effort or effort. And we'll be using, well, in general though, consider data packages that allow you to read data, especially if they can read across data sets. Like I said, we'll be using Olmo. Olmo is a community resource in Python. It's open source, of course. It focuses on water and climate data. So surface water, some groundwater, and climate data. It wraps a lot of the underlying complexity from each of these services into essentially an API that is a lot simpler and more user-friendly than what you would encounter from the original source, because it makes some of the assumptions behind the scenes. So it can make life, it's not that it opens the door to access to any particular data set that was inaccessible before, it just makes it easier. And it's a single package where you can get different data sets. I've listed a few others that you might consider, and I won't say anything about any of them because I never used them, but feel free to explore them. Now we'll move on to hands-on live code, examples of actual usage of the stuff I've been talking about in Python using Jupyter Notebooks. I know you've been exposed to Jupyter Notebooks already. The area that we'll be focusing on one particular geographical area, and that's the Southeast US. Why? Because Yifan is a PhD student, and that's his research area. And that seemed like a perfectly good example or a good reason to focus on that area. I know nothing myself about that, the sites I'll present. We'll be focusing on surface water and specifically temperature and to some extent discharge and water quality. We'll be running Python code, again, live, using Conda. You'll be hearing more and more about Conda as a packaging system to maintain environments for Python packages and a collection of a setup for Python. We won't be teaching you how to use Conda here, but just be aware of that. And obviously, we'll be using Jupyter Notebooks. We prepare everything that you'll be seeing here, including this presentation and the notebooks and the Conda environment file so that you could set this up on your own, will be available at this GitHub repo. And I said will because right now it isn't, but by tomorrow or definitely by Monday, it'll all be ready. And so you can check back on Monday or maybe an email can be sent. Okay, so now we'll split into two use cases. The first one is on river and reservoir water temperature by Yifan, and then I'll follow up with follow-up.
So, hi everyone. I'm Yifan Cheng, now a fourth-year PhD student in University of Washington. I'm working in computational hydrology lab. So now I'm just gonna give a.
There.
This one.
Oh, sorry, I just wanted to. There you go.
Oh, yeah. So today I'm just going to talk about some basic statistics and how we calculate in Python through a simple case study on regulated river temperature, which is a very important variable in water quality. So in this case study, I'll give a basic introduction, background information about what research questions we're going to mention, what's the study area, and also I will introduce how a simple recap of visualization, just how we mapping those USGS sites in the map, and how to download the USGS data through the Python package WOMO, which Emilio just introduced. And also I'll make some simple analysis. So,
increase the font.
Oh, sorry.
A bit, 1 or 2 steps.
Okay. So in regulated river systems, the dams will impound a large water body and create deep reservoirs. But the surface energy will only warm up the top layer of the surface, and the bottom layer of the reservoir still stays cold. So which creates very stable thermal structure in the reservoirs. And for those reservoirs generating hydroelectricity, they will usually outlet the flow from the bottom layer so that they can gain a very high water head to generate more hydroelectricity. So the reservoirs will have a cold impact on downstream river temperatures. So today we're just going to look at the research question is how is the river thermostratification going to affect the downstream river temperatures? And I specifically choose the study area of Beaufort Dam, which is a very important dam in southeastern United States. It provides hydroelectricity navigation and also flood control of Chattahoochee River. And it's also a very important water supply for the city of Atlanta. In this In this study, I manually pick 5 USGS sites. And so in the next case study that Emilio will talk about how we can get a query of USGS sites, filtering the locations and also what variables you want. So I manually pick 1 site upstream of Beaufort Dam and 4 sites downstream of Beaufort Dam. So here is the USG. Okay, let me just clear the all outputs. Sorry, so that we can get a better idea of what's happening here. So the first is just like importing the modules we want. And this part, I just load the USGS sites. And so first, if we want to collect the site information, we can use a function named getSites in the WOML packages. So what we only need to provide is the USGS sites number, and the format it will return from from this function is WaterML1, which is provided, which Emilio just mentioned. It basically is a dictionary format, and it contains the site information, including the name, network, and also the location information. So when we first get the USGS site, the first thing in our studies is to visualize and map. We can map all those USGS sites in a spatial map and see their locations. So the first thing here is I get the site latitude and longitude through the function called getSites. Okay, this is done. And then this is a simple recap of what we learned in the last seminar given by Tony. So basically, we download, so there is state boundaries, country boundaries, coastlines. Those are already provided in the natural Earth data set. You can just directly access it through the Python package called CartoPy. I won't go into detail of the code here. And then after we run this code, we can just see the spatial map of those 5 sites and also the rivers and then Lake Lanier. So so the red dot is the site upstream, and then there are 4 sites. We name it downstream 1 to 4 as it flows downstream. Then we just use a function in WOML called getSitesData here. To just download the USGS sites. We need to pass some variables, including site code, which is the USGS site number, the parameter code, which is the variable. But here we need to pay attention is the variable also the variable can possibly have different units, like temperature can be Celsius or Fahrenheit. They use different parameter code. And there is also a link to all the USGS parameter codes here. And also there is statistic code, which basically means that you can get like the daily maximum temperature, minimum temperature, or daily mean temperatures. So here is an example of how we download the USGS data through WOML. So there is one thing to note that you need to pass the starting date and end date. Otherwise, it will just give you the most recent single day. And then let's take a look at the data. So it basically provides you, first is the metadata in WaterML format, and then it also provides you the time series of the stream temperature data. But you can see that all the values here are in string format. And usually what we deal with is not, we don't usually deal with data in dictionary format. So the first thing here is to convert the data format to Pandas Dataframe, which we talk a lot here. So the first thing is to create a data format, and then we change the value from string to float. And also we change the date, as Emilio mentioned a lot, we need to change the date to the date time format. And we set the index to date, and then we delete all those columns that we don't want. So here we can take a look at what's the date look like. So the index is the date. as we said above, and also the variable name is just the USGS site number. So in the next section, we just like download all the USGS data through a for loop. And for here, we concatenate those data frames together so that all the stream temperature data for 5 sites can be summarized in one single column. And then this step, we just drop the rows with no values. And then here is how the data frame look like. So you can have the index with time period, and then the column names to be the USGS sites. So next I would do some simple analysis. The first thing we get the time series data is we usually just plot the time series. So there is like 2 plots that we do normally. The first thing is do a line plot. The syntax is pretty simple, just PLT, which short for matplotlib.pyplot. And also there is a scatter plot. You can just use plt.scatter. And we recommend to do the scatter plot when the data is discontinuous. So here we just plot use the scatter plot, and then we can self-define the label as we like. So as we here, so the color here is the same as we defined in the spatial map. The red one is the stream temperature upstream. In the upstream area, we can see this has the most significant seasonality, and we can see that the blue scatter plot is the stream temperature immediately downstream of reservoirs. It has very depressed seasonality, and also the summer temperature is about 15 degrees compared to the upstream ones. And with the river flows downstream, the stream temperature gradually increases, as you can see here. So this is a very interesting phenomenon that thermal stratification can affect downstream river temperatures. So the next, I want to simply tap about data selection and indexing. You can choose, because like data frame is a 2D data. So you can either choose a single column, or multiple columns through just the data, just put the data sum and then the column names in the bracket. So for here, you can choose like the single, the first USGS sites, or you can choose like 2 USGS sites. And you can also select index by using dataframe.lock function, and also put the index in the bracket. You can either choose single index list of indexes, but also you can choose the slice of date, which use the function called slice, which basically will provide you all the available data in this data range. So here is a single index, like just the first day in 2016. And then the select index, we can also provide pass the list of list of date, and then it will return you the first month of 2016. So the list one is select a data range. For example, we here put 2014 to 2016, but we don't have data for 2014, so it will only provide you the data available in the data sum, in the data frame. Okay, so the next is some basic statistics. We can calculate like some simple statistics like maximum, minimum, mean, median, standard deviation, and etc. And all those functions are already implemented in Pandas. So you can simply use a data frame dot and then the function or like the metric you want to look at. So here you can see because Pandas data frame is a 2-dimensional data, so you can either calculate like column mean or calculate the row mean. So here, if you put the axis equal to 0, you can get like the median value. So here you can get the median value for each site, and throughout all the time series. And also, if you put the axis equal to 1, you basically can get the median value for each day throughout the 5 sites. So next part, I will talk about data aggregation, and this is like the most commonly used in our studies because, for example, if you so if you want to look at if you get like hourly data, you want to look at, for example, you don't want such high resolution, you want daily data or monthly data, you can probably use resample. And this is, resample is used to upscale the temporal resolution, like frequency conversion. And the group by is basically just we use to split the whole time series, a whole group into different subsets based on some metrics like the same month or same day of the year, and then combine those results into the subsets and apply some functions to it. So here is some example. The first is, for example, if we want to calculate mean monthly river temperature, we can use resample, and the M here means months. So here, then we can get like the monthly stream temperature, given the data is daily. And the next, for example, if we want to calculate the maximum river temperature in each month through all the time series, we want to select all the data through in each month and then calculate the single value for individual months. And here is the example of it. So then you can see the maximum river temperature in June for each site is like here, is shown in this data frame. But sometimes we also need to combine resample and group by to do some calculation. For example, if we want to calculate the long-term mean of monthly mean stream temperatures, so we first need to resample it into monthly time scale, and then we use group by to group by different months and then calculate mean values. So here's the result. There's some like simple implementation, and the first thing we can look at, for example, if you want to look at the variable like interannual variability, you can basically just use resample to upscale the time resolution to annually calculate the mean annual stream temperature, and then you can use the plot matplotlib to plot the time series, and then you can also self-define the ticks and also the labels you want. So here is the stream, the interannual variability of stream temperature. You can find the downstream 4 sites have very strong correlation, which is a little bit different than the upstream ones. So the next one is seasonality. So first here we just calculate the mean monthly stream temperature, and then we use group by to calculate the upper boundary, the lower boundary, and the median values. So here and in the plot, I plot a line plot for the median value, and also plot a single shape for the upper boundary and then lower boundary. So this is also the way how we usually deal with uncertainties in the seasonalities. So the next, I will give Emilio to talk a little bit more about the stream.
In the other one, that one.
About some implementation of WOMOS.
So I'll complement what Yifan talked about and go back to that step of searching for data. Yes. Let's see, we'll clear all the output so that we can run it as we go. Here are the libraries or modules that we will be using. And first we'll, Yifan had a fixed set of stations he already knew he wanted. We'll take a different approach here. We'll do a search in an area. In this case, based on HUCs, it's an important national division of watersheds that comes in different codes. In this case, we'll be using the HUC8, a specific HUC8 code in the upper Little Tennessee River. I've created a GeoJSON file, it's a spatial format, and put it on GitHub. And one of the really nifty things about, there are many nifty things about GitHub, but GitHub can render certain things in smart ways. So just by putting this file, this GeoJSON file on GitHub, we can actually get a simple but very useful interactive map. So that's the area that we'll be looking at in North Carolina, Tennessee, etc. So north of where Yifan was looking at. What do you do to? Okay. And I've selected, that's the code, the Hockade code. What we'll be doing is we'll be using get sites, NWIS get sites from Volvo, the same thing, the same function Yifan used, but we'll be using it in different ways. Instead of passing a set of sites or one site, we'll be passing a hug code to return all the NWIS sites in that area, in that polygon. Oh yes, thank you. Thank you. Okay, so now we'll run it, and it's making the request, and we got everything else. What does the response look like? Typically, when you get something like that for the first time, you want to explore it. So I'm going to look at what type it was if I didn't read the documentation and what the length of it. So I got back a dictionary, and it's got 20 elements. I'm looking at the keys of the dictionary only because often what you get back can be large, and so it can be overwhelming. So I tend to be careful. But here's just an example that what you would get back if you try to print the whole thing. Okay, so. Okay, so now out of those site codes, I'll pick one. It's not random, I've looked at it before, and I'll explore that one. Not by issuing another query, but just by looking at what I have, the dictionary that I got back. So that's the site information I have for that one site code. That also lets me look at the structure of how data are organized. For example, latitude is embedded within another dictionary within location, so that's kind of a hassle, but no big deal. Now I'm going to process the data to make it more like a flat table, at least for the stuff that I care about. And latitude and longitude are certainly things that I care about. So I'm going to create new latitude and longitude variables by pulling them out from the nested dictionary. And I load them into a dictionary and look at it. And what I get is not what I was hoping for. I was hoping that each row would be a site, but it's kind of reversed. The column is a site, and all the attributes are rows. So I'm going to flip it by doing a transpose. And see, Pandas magic. Now I've got it in the shape that I want, and I just gonna need to do a few final cleanups. Latitude and longitude are coming in as strings, so I need to convert it to values, so float types. I'm gonna convert within Pandas to latitude and longitude to float, and then drop columns. And now I've got exactly what I want. Okay, so what does it look like? First, I can do a quick summary by site type. NWIS has categorized the sites into a type, and it turns out that I have two types within the 21 sites that I got, or 20. ST and AT, I have no clue what those are, but if you go to the documentation or go to NWIS, you find a wealth of documentation. There is this page that will explain all of those, and it turns out that those two are stream and atmosphere. Now, we could use, if you wanted to be smarter about the query, you can actually pass a site type into the get sites. But we won't be doing that because we're only dealing with a small number of sites. Okay, so now we want to see it. And what we're going to do, we're going to use this Folium interactive map that Tony talked about last week to plot, take that data frame or those results and give me a nice interactive map that allows me to explore within the notebook. So those markers are what I got back. The colors, the blue are streams and the gray are atmosphere. I did that here, blue if roadside ST. And I just picked some attributes to show in the pop-up. So just so that to help me figure out what side they are and which one I might want to look into. That's the one we explored initially. Okay, that is all that I'm going to do with NWIS, and that hopefully complements it. You could view it as sort of a preliminary step that Yifan did before he got going with his notebook to find the sites he needed, or what you would do, I guess. But I'm not going to pull data, time series data from NWIS because Yifan already did that. But now that's just NWIS. NWIS is fantastic, but it's not the whole world. There's plenty of other data out there. I'm curious then, what other data might there be within that Hockade besides just NWIS? So for that, I'm going to do go to model my watershed and navigate to that HUC. And I'm going to do that. Oh, I'll need your help. I don't know if you uploaded a GeoJSON file. No. Okay. I will. I was going to upload originally a GeoJSON file that this application allows you to do that same GeoJSON we just looked at, but instead I'm going to do something different. This system, because it's focused on watersheds, allows you to select data based on HUCs. So I think, yeah, this is the HUC I'm interested in. So I select one. And now it's going to do a number of things. One of them is it'll give you access to this useful watershed summaries, but we won't care about that. Here, it allows you to query across 4 systems, as I mentioned earlier. So I'm going to, let's see, streams. You can type different text and just do explorations. And you can see HydroShare, CUAHSI, WDC is an old acronym, but basically the HIS, CUAHSI catalog. Synergy is this other system, the broad system that I mentioned briefly, and the water quality portal. So you can see this is what I'm getting back from HydroShare based on a bounding box. Each of the system has strengths and weaknesses. Some of them only allow a bounding box. Others are really broad. Like Synergy will give you a lot of almost extraneous data, kind of like Google search, I guess. And some of them may have errors, like San Diego. What the heck is San Diego doing here? This is the CUAHSI system. This is just like going to HydroClient, except they're folded into this other system, and we can explore data here. The data set that we looked at briefly is here, I believe. So let's just explore it. And this is a system that's nice for doing that easy exploration. So here you can see that it brings all the variables from that site that is from USGS. So you can get at the same information by going to NWIS or by going to HydroClient, but the way it's presented will be different in each of them. Here you can see all the variables, which HydroClient will call series, in one place. And you can get quick plots. Now, this is not a full-blown visualization application. It's just for getting a feel for what you're getting, what the data looks like. So let's look at temperature, because that's what Yifan was interested in. Over a year, it only lets you look at it 1 year. That's part of the limitations. And I want to look at turbidity, because that's more water quality, more fun. So you can see all the spikes. I can play around with, again, the emphasis here is on quick and easy visualization, not data download or anything else. But I can probe further by, in the case of NWIS data, and it provides a link to the data source. Can you go back to where I was? Sorry.
Which one? This one?
Yeah, that one. Sorry. Okay. I can now, one of the reasons I went to this site is that there is this HUC. So there is this long-term field site called CUAHSI, or however it's pronounced. And so I'm curious what data we get about CUAHSI, that area. There's an LTER station in that region. We've got climate from Ncdc, as well as NWIS, both of those coming from the CUAHSI HIS, which again brings the advantage of consistency. Data are presented in the same way. And so both within HydroClient and here, you can visualize it exactly the same way, even though they're coming from completely different agencies and different sources. Groundwater from NWIS and a bunch of other stuff. Synergy will have various geology maps. HydroShare, it's kind of interesting. It'll, let's see, see that, okay. What it got us was 2 model results, or 2 model runs from CUAHSI that are flagged as CUAHSI. And Water Quality Portal, again, every system has pros and cons, and it'll give you some stuff, and it's kind of limited, but the way, if you go to the Water Quality Portal, the search interface, it's kind of clunky, but you get full access to everything. Here, the search interface is fast and easy, but you only get limited information. And so hopefully things will get better with time, both in this system, as well as the Water Quality Portal and on all the individual systems. Can you go back to the notebook? Okay, so And now I am interested in pulling in data from CUAHSI using Water One Flow, so not the NWIS, but going directly to CUAHSI, pulling a time series. So I'm going to play, and I don't want to do NWIS because that's not we can already get it that way. So I'm going to go to oh, sorry, that's not what I meant to click on. This is a resource. Can you go back that you might want to look at that does kind of like the NWIS get sites on HUX that I presented, that it'll talk more about the HIS central querying and present code for doing that. That's from Tony Castronova, who presented this seminar about 2 weeks ago. What we're going to do is explore on HydroClient for quote unquote nearby sites, because they're not so close, that have oxygen, dissolved oxygen, and that is from a source other than big federal agencies. Just to give you a taste for the diversity of sources that HydroClient brings in. So this is the web application that I've been talking about, and I'm going to zoom in the area we've been looking at. Let's see. We'll make it pretty broad. Every system has limits, so there's a limit here in how much data you can query on. If you zoom into the whole US, it'll tell you, no, that's too much. I can't return that because it's just too much. Now, I happen to know about this because I did my homework about this data source. You can see here that all the different data services that are wide variety, Arizona, University of Washington, and so on. I know that that's the one I want. So I'm saying here that I'm going to only search on that data source. And I can search on keywords. And I want dissolved oxygen. And because this system, even though it's coming from different sources, it maps different names for dissolved oxygens and variables. We can actually do this. That's a lot of work, and few systems can be that consistent. So I've got this 6 sites. I'm going to, well, the search is already done. We could probe here, but one thing that is interesting is that if we go to filter results, you see that it's also organized into this set of parameters of vocabulary. So we could navigate and filter things further by, well, we know we want oxygen, but different things. We're not going to make select, but you can check and make selections. Okay, so now we're going to drill in, and here is this rubber bird location. Each of these is HydroClient. You can see the information, the source. Where is the, sorry, how do I'm looking for a scroll bar here.
No, you can just,
oh, there we go. So you can see all the information about each variable or series, the start and end time variables, and you can see these codes, service URL, site code, and variable code. I've copied those, or I will copy them into the notebook. You can also select this and view the data and explore it fully without the limitations in Model My Watershed. That takes a while, so I'm not going to do it. Basically, select it and go to select action and so on, and then it gets loaded into a time series viewer app from HydroShare. So now we're going to go back to the notebook. Okay. So after doing that, I copied and pasted this network code from what I was seeing there, and the site code. I'm going to pass that into the Olmo CUAHSI Water One Flow get site info and issue a web request, just like the NWIS request that Yifan and I issued. And now I'm going to start exploring it. So it's a dictionary, and it's got this elements. If I do site info, it's probably large. You can see all that information. And that'll be a reference you'll need to have if you want to drill further. But you can see there's a lot of metadata. There's no data here in this request. It's just metadata, but very, very rich. And that's the advantage of one of the advantages of the CUAHSI system and WaterML. Okay, now we're going to pull in the time series data. We got the code that we got from HydroClient. I know that that's the structure. That's where the variable information is at, and there it is. For the variable we're interested in, dissolved oxygen. So we can get names, units, and so on, and time periods. After sort of paying close attention to that, I know that I can get the start and end times this way. And now I can issue, now that I have this information that I extracted from get site info, I'm going to put it in another request to actually get the time series values. And so now we issue another request from Olmo that queries the HIS system and tada, it's done. And here are the keys. This function just packs the processing steps to convert datetime into a Pandas datetime, to rearrange data, etc. So, and then I can just issue the function, and now I have a time series data frame for the variable that we're dealing with, which is oxygen. And I'm going to do a simple plot. Rearrange or grab all that metadata, the site name, variable units, and so on, and all the stuff we got remotely. I didn't hardwire anything except which site and which variable we wanted, but we can pull in that wealth of metadata as part of our exploration. Here is the name of the variable, the units, the code, and the long name, and of course this is a proper datetime, and we've got time series. Now, because this is an Ohio sanitation agency, they've got their own specific needs. They're not there to monitor long time series, but rather they're looking for harmful algal blooms. So this is 2 months. And we may have, I don't know if you still have 2 minutes. No, we don't have. I'm just going to open the notebook just to show it to you, because we have, or I have run out of time. And you can check this out after we send you the links. This is for Neon, and in this case, we're dealing with not something we can do via Olmo. We go to the request package to use this REST API. They have good documentation, but we start exploring it by issuing a sites request into the REST API. You can see that. And then same thing, start exploring, cleaning up, deciding where we want to see, rearranging into, in this case, a geodata frame, and then more rearranging of the variables that we want. And we add LTER because this is a broad look at, and then we use volume again to have this broad look of sites in that area from field observatories. And then we bring those three together with one Gleon site that is hardwire, and we get, again, a volume interactive map with sites from Neon, sites from LTER, and the single site from Gleon. And there's more stuff below if you want to probe further. It gets more complicated, but enjoy.
Wow, Emilio and Yifan, thank you so much for the wonderful seminar. We've learned a lot about where to find water data sets within Google data sets and the CUAHSI hydro clients, and how to plot them and how to explore them. So thank you so much. We are a little short on time, so maybe 1 or 2 questions if you have any before we wrap this up. So feel free to type your question in the text box. I guess we don't have any questions, so thank you again, Yifan and Emilio, and we'll see you next week. Thank you.
Thanks.
Thank you.
Sorry for not leaving any time.